Hello, and welcome to the first series of the webinar Advanced Modeling. This is the Allplan Bridge solution that we're going to talk about today. Already for all the existing users, we know that this is the parametric modeling, structural analysis, detailing, and design in a single beam solution for bridges. But this is the webinar series Advanced Modeling, and this is the third part. And today we are going to talk about something other than bridges. And this is going to be the webinar about other structures that we can do in the infrastructure. So I would just like to quickly introduce myself. My name is Jan Oster. I'm a civil engineer from Slovenia. I have been part of the infrastructure team now for almost 3 years. I'm here as a technical consultant. And as you can see from my experience, I have experience in bridge engineering, either in modeling or analysis, consultancy and support on bridge projects. I'm also involved in product management and also involved in software trainings. In the next step, I would quickly like to go over the agenda so that we know what we're going to see today, what we're going to talk about today. First, our agenda. So this will be at the first point, we will quickly do a recap about the introduction and about the principles of the Allplan Bridge solution. And in the next steps, we are going to see a very nice visual presentation of how to model terrain, retaining walls, tunnels. We will share a few tips and tricks how to more efficiently model foundations. And maybe the last point that is not really part of the infrastructure, but it's also very interesting to see that we can also do something completely different like cooling towers. Okay, so I would suggest that we just dive into the presentation. And just first of all, I would like to talk about the principles of Allplan Bridge. So we know that at the heart of the BIM process should be a complex, a strictly parametric digital bridge model. We know the quality of this model governs the straightforward usability for differing purposes between different disciplines and phases in the life cycle of the bridge. Of course, what is also very important is that the time axis needs to be considered as well in this process. Additional requirements is the direct use for visualization, quantity takeoffs, equipment, detailing, drafting production, and of course, at the end, the maintenance of our object or model. Other key points are an intelligent and self-explaining user interface and an open structure allowing easy communication over different platforms. The central BIM model for any type of bridge during the life cycle represents the source of truth for all project teams. Such BIM system assure compliance with deadlines, early detection of errors and their correction, and subsequently higher cost security during the process. So we know that for the bridge industry, only the open BIM is acceptable. It means that the neutral data formats like IFC or BCF across all disciplines should be used. So just now at this point, a quick recap about the Allplan Bridge solution. We know it has been told many times, it is modeling, analysis, design, and detailing in a single solution. We know it's the worldwide first fully integrated BIM solution with a single parametrical 4D model for modeling, structural analysis, design, and detailing. As we know, this consists of free software in one package. This is Allplan Bridge. This is for the parametric modeling and the analysis of the bridge. Then we have Allplan, which serves as a detailing software, which allows us to model reinforcement, enrich the model with attributes, do quantity takeoffs, create reports, create drawings. And of course, at the end, the cloud service, BIM Plus by Allplan, which is meant to share the project with your coworkers, with people who are involved in the project. The next step, just a few words about Allplan Bridge. What are the key factors of Allplan Bridge? It's the parametric modeling that makes it so unique. There are three main parametric elements. One is the axis, the second one is the cross-section, and the third one are the variations that can be applied. As we know, the axis is something that during the design process can change at any time. So the alignment from the road engineer can change at any times. And it's important here that also the model that we have created till a certain date also accept these changes and all the changes from the alignment are applied to our bridge model, from the geometrical model to the analytical model. The second one is the parametric cross-section, which we can say it's a responsive or an arbitrary cross-section, which allows changes at any time. So we can, for example, as we see in this nice model on the right side, we can easily, for example, in this case, adjust the height of the cross-section along the alignment. And of course, this is what we're doing with variation, variables, variation tables, and formulas. So in any way the user would like to do this, he can do it. We provide an exact geometry, and what is the most important part is that modifications are possible at any time. And these modifications will be displayed through the whole model, from geometry till analysis. So, but today's focus of the webinar will be something else. Because we were asking ourselves, is it only for bridges? Is Allplan Bridge, because of the name, we have Allplan Bridge, and most of the users are using it for bridge projects, but is it only for bridges? And my answer to this is no. Because at this point, we have this parametric technology at our hands, which allows us to model any kind of structure that requires an extrusion along an axis. And as we know, these parametric models can be changed at any time. Any changes can be applied, either is the alignment, either is the cross-section. And today, we are going to talk about other infrastructure objects, like terrain, which is a very important part of any infrastructure project. We have retaining walls, which are also a very important part. And if you're talking about, for example, about highways, bridges, there is also tunnels, because sometimes we can't do a bridge. We can't just go with a highway or a road through a very large hill, a very hard rock, then we need to do a tunnel. And of course, at the end, we're just going to talk about cooling towers and foundations. Just a quick reminder. So what you will see today, because this is an advanced modeling webinar, but still, the steps shown in this presentation do not require any special knowledge. So anyone who is familiar with creating a cross-section, creating an axis in Allplan Bridge, will be able to do all of these models, all of these, let's say, special structures that we're going to show today. On the right side, we just see one of the small examples where we have a combined model of two retaining walls, a road structure, and terrain. But we will now start to go more into detail on this. So the first part is the terrain modeling, which will basically be included in every other object that we're going to show further on in the webinar. So I think as the first step, it's most important to understand how we model terrain. And now just to quickly go through this terrain modeling in Allplan Bridge, how we can do this. We know that terrain in infrastructure project is a key factor for preparing the finished model. We need the terrain. And it's important that the terrain follows our object of interest, or as we like to call it, the alignment. And it's also very important that this also changes to the alignment. So that also, for example, this terrain, let's say, in a certain boundary around our object will apply to changes. And we know that at this point, existing Allplan Bridge functionalities can be used to create a terrain model along our longitudinal object. So the basic functionalities we're going to use are cross-section functionalities, and this will be parametric lines and points that you already know them. You might recognize this. This is the action bar for the cross-section creation. And on the left part, we have these most important tools that we're going to do to create our terrain model. So these are the parametric lines and points. And there we have all sorts of functionalities there, where we go from parametric lines, where we can place a parametric line over a direction, parametric line between 2 points, different types of line per angle, line by relative factor, or by just placing a parametric point. And these actions allow the user to create this basic parametric outline for the terrain model. The same as with other models, also additional steps can be taken to apply changes to the geometry along the provided axis. And now we will see our first example how we start creating the terrain model. So by using the tools that I have shown on the previous slide, we can define the outline, which is here represented by these parametric lines, and the outline of my terrain model will represent, as you see on the picture, the red parametric lines, where I have defined an offset of 25 meters to the left side, one to the right side, and then additional offsets to the top and to the bottom. Of course, what we also need to do, what we do with our bridge project, is we need to make use of our boundary tools, which will determine the outline of the terrain. So for this, we use the boundary tool. We know we have 2 or more possibilities how to place these boundaries. So we just use the standard one that we're using also for bridge projects. So according to this outline that we have defined on the left side, we can define the outline of our boundaries, of our terrain, as we see on the right side. But we would like to make this terrain a bit more realistic, because now we see just these linear transitions between different points or intersections. So boundary actions also allow us to modify the created boundary with tools like rounding boundary points. And as you might remember, you were probably using these functionalities very often, but for this case, we are going to use the round boundary point action. And once we apply this to our model, we can see that we get a more realistic representation of the terrain model. What will be the next step? The next step will be applying a structure unit to the created terrain model. The cross-section can be then extruded to a solid element. And here we see, once we have applied this structure unit to our model, we already see that it got a nice green fill, and we know that the model is prepared for extrusion. On the right side, once we create this girder, once we create this 3D model, we see our terrain model on the right side. But this is not the end of this, because the same solid object can be then exported to Allplan Engineering for further work, let's say for further detailing. This is the first model that we get into Allplan Engineering. This is port that has no data at all. But by making use of additional visualization elements that can be applied to the 3D body, we can create a nice, let's say, grass representation of our model. We can also, for example, for geometrical purposes, create a soil profile, which can already be prepared in Allplan Bridge. And for this, I have used the same terrain model, and you've seen I have prepared now basically 2 soil profiles. I could go more into detail on this, but I think for the sake of the webinar, for the presentation, it's enough that we have 2 different soil profiles. This is how the model is then shown in Allplan Bridge once it's extruded. And of course, once we apply different visualization features, we see that we have a nice grassy representation on the top side, and to the lower side, we have this nice earth representation. At this point, I will also show a few projects submitted by customers. And we have a very nice submitted project from the company Sagasta from the Czech Republic in the project Overhead Crossing Nisberg nad Ohry. In this project, they created a nice looking bridge model, but they also used Allplan Bridge already to create a nice terrain model. As we see in the first picture, this was created in Allplan Bridge, and this is the model then exported to Allplan Engineering. As we see already, some visualization features have been applied to the 3D model. There is the same model, but just from a different viewing angle. And of course, we can also create nice visualizations, nice renderings like this with the terrain model created in Allplan Bridge. Okay, so now at this point, we know how to create, for example, a terrain model. We've seen a few examples, we've seen some user examples. The next step are retaining walls. This will be also a very visual representation, and I have decided to focus on 4 types of retaining walls here. These are going to be gravity walls. These are going to be piling walls or driven walls. These are going to be cantilever walls. And last but not least, which I think will be the most interesting, is anchored walls. But we will get more into detail just in a few minutes. So first of all, I have prepared, let's say, a schematic representation of a gravity wall as a cross-section. I have also included in this part terrain, and I have included the gravity wall as a concrete object. The first step is to recreate this model from this schematic representation, to recreate it in Allplan Bridge. In this case, it's maybe a pretty straightforward approach. Because we are using the tools we already know, we use parametric lines, we create the boundary, and we apply structure units. So there is nothing special at this point. This model, as a 3D model, can then be extruded in Allplan Bridge. And of course, we can send it then over also to Allplan Engineering, apply some visualization, and use this model for additional detailing. The next one are piling walls or driven walls, however we would like to call them. Also, first a nice schematic representation. This one seems even more easier than the previous one. So by just making the use of this basic cross-section functionalities, we create this cross-section in Allplan Bridge. Of course, the model is then also extruded in Allplan Bridge, and the model is then sent to Allplan Engineering. Some visualizations are applied, and we get this nice model. The next one are also a very common type of retaining walls, are cantilever walls. First, also we see again the schematic representation. And of course, by using the same functionalities as with the two walls before, we create this cross-section in Allplan Bridge. So these are just a few ideas how to make use of this amazing technology that we have already at our hands, but for something different. So of course, we extrude this model in Allplan Bridge, and further on, we export it to Allplan Engineering, apply visualizations, and go into further detailing. And as I mentioned before, maybe the most interesting will be anchored walls. And first of all, the schematic representations. We see it's basically a driven wall, but it has soil anchors at the behind of it. And we will see how easily we can apply all of this already in Allplan Bridge. So we make use of this new technology that we have. So as you know, as existing users, you know that we have already these smart placements, or placements, how we call them, that this was already present in Allplan Bridge. But now we have also the possibility to place parametric Python parts. And we see at this point, okay, we have created the cross-section of the piled wall, of the driven wall. But we see in this case that we have applied also the placement in a certain direction where our anchor should be placed. So this is now an, let's say, parametric definition, and also these anchors will apply to changes in the model. And we will see just in a few steps. But before we export the model, we need to prepare the anchor model in Allplan Engineering, where we save it to our library. The next step, once this is created, we need to assign it in Allplan Bridge so that it knows its position, its parametric position on the model. This is now the model exported. We don't see the anchors yet because we need to apply some transparency to the model. Once we apply the transparency, we see at the back that in the soil, we have these soil anchors. Might you see the wall? We also see a very nice representation of all these anchors at the wall. And of course, we can either take a look at smaller segments where we have just one column of anchors. But we can always combine these models. So in this case, I would like to show a combined model of a few retaining walls where we have a cantilever wall on the top right, there I have a road structure, and then I have a driven wall, a driven anchored wall. Now this is a bit bigger model that I have extruded through the whole axis, and we see this representation in Allplan Bridge. Then the visualized representation in Allplan Engineering. And of course, with applied transparency, we can also see all these anchors that have been applied to the anchored wall. At this point, I would also like to show you some real project examples. This one was created by our colleagues from the United States of America, from Allplan Incorporated. And this is an existing project. This is a real project where they also made use of creating retaining walls. So this is not just a bridge. We see a road structure, we see retaining walls. So we see all kinds of infrastructure objects in this model. There we have also some projects submitted by customers. And this is from the company Benzinger Partner from Switzerland. And the project is Teilausbau und Sanierungsstraße Lehnkonstruktion Obernas. First, I would just like to show a few cross sections of the retaining walls that have been used in this project. But of course, I think more interesting will be to see the 3D model, how it looks like. So I have first picture of these retaining walls, but we will see what's interesting about this structure once we see it in the 3D visualization. But before we come to the 3D visualization, I would just like to show a few drawings that have been produced from this model. So we have a few sections that I would like to show here from the retaining walls, from the supporting walls, and also some nice visualizations from this part. But of course, I think which one is the most interesting is how this structure looked like and where its position was. So it's really amazing to see what already existing users are doing with this software, and that it's not just used for bridges, but also for other infrastructure objects. But just a quick reminder about these combined models. We know that sometimes these big models can produce crashes in the software, but maybe not the kind of crashes that you would expect. It's more like car crashes. So be careful of that. And of course, a quick reminder, you know that we can always position elements like cars, trees, also parametrically on the bridge. Because if we change the alignment in design phase, it's fine, but not after the construction is finished, as it might cause some unexpected behavior. So keep in mind that parametric position element is a very useful tool that you have at your hand. So the next step will be about tunnels. So tunnels are a key part of the infrastructure. And as we know what tunnels are, these are underground passageways. They're dug through the surrounding soil, earth, or rock, and usually enclosed for the entrance and exit at each end. We know that Allplan Bridge was mainly designed for bridge engineers, but its extensive parametric modeling capabilities allow users to create also other infrastructure objects. And just keep in mind that creating tunnels in Allplan Bridge requires no extensive additional training, but just needs to make use of existing modeling features. So we're going to focus on 3 types of tunnel cross sections. We will start with simple one and then go to the more complicated ones. So first one is just a simple rectangular cross section. It might look like a hollow box girder bridge, or it's just turned around. So it's the same principle to create this. So once this 3D model is applied with materials and extruded in Allplan Bridge, we see this nice tunnel representation. So this is an easy one. Keep in mind, we will go into more advanced ones just in a few minutes. The next one are circular cross sections, which are also very simply applied by using the circular boundary tool, and the same extruded as a 3D model in Allplan Bridge. And then with applied materials, we see a nice representation of the tunnel in the model. But now we come to these more complicated ones, to the complicated shapes, which are, let's say, elliptical or typical horseshoe shapes. And I would like to show you 2 methods. The first one is by boundary thickness. And I will show you in a few steps how this can be applied. So first of all, we start by creating our outline where our horseshoe-shaped tunnel will be placed. So this is here defined with the red lines as we see in this picture. The next step is we are going to make use of boundary tools, as we've seen already in the previous model or in the terrain model. And we create now first step of this shape. But to get, let's say, the correct elliptical horseshoe shape, we will also apply the rounding of the boundary line at some point. So once we apply this functionality, once we define the correct rounding values, we get this nice horseshoe representation. So once we have this nice outline of our tunnel, as we see here, is the next step that we apply boundary thickness to it. As we see, these closed boundaries have the possibility to have a thickness applied. And this is the end result that we get from this boundary line. So here's just a 3D representation Allplan Bridge with additional model data. The next one, which is a bit more challenging, but can also give you an idea how to do it or to do a bit more complex shape, and this is by intersection method. So we see it might look scary, but it's not, because it's a process where we create lines by angle, look for intersections between them to create the correct elliptical shape. Again, this model is then extruded in Allplan Bridge, and with applied materials, we can see this nice representation of concrete also already in Allplan Bridge. We have also some tunnel examples that already have some equipment modeled inside. So we see on this cross section, we see that it's not just this typical horseshoe-shaped tunnel, but we also have a road structure inside. And if you might take a look on the bottom right side, we also have some gutters, so just to get the water out of the tunnel. When we apply the materials and extrude this model, we already see this nice representation with modeled equipment on the right side in Allplan Bridge. And of course, once we apply also all the materials, we get this nice concrete representation. So as you might see, there are no boundaries to what you can do. So you can just simply decide, okay, I just want to shape the tunnel, or I can give additional data to it, like the road, the gutter, or anything else that I would like, which will also apply to changes to the alignment. But of course, we need terrain with tunnels. So for this, we have created the terrain model. And by using these Boolean operators that you already know, where we can remove one boundary from another, we create this nice terrain shape where we have inside the place, the position of our tunnel. I have decided to use the tunnel shape that was created by the boundary thickness method and insert it into this model. So we get this nice interaction between the terrain and the 3D model of the tunnel. At this point, we also see how it interacts between the model, how it interacts with the terrain. Of course, also these models can always at any point be exported to Allplan Engineering, where we can use them for further detailing. So at the first image we see where, as we have seen already, I have applied already some visualization features. So we have a nice grass visualization of the terrain, and at the bottom we have a nice concrete visualization of our tunnel model. The next step, what we can do, we can create sections that we see on the top right, where we can apply dimensioning lines. We could do all sorts of drawing preparation at this point. As we see at this point, we have a good representation of the terrain model and then the tunnel model inside. At the bottom, we see one segment of the bridge model, and we can either do this in two ways. And the most appropriate way would be to make use of the construction schedule in Allplan Bridge already, because once we set up the steps how this tunnel will be constructed, also these construction steps will be exported to Allplan Engineering and can be then used for further detailing. The second step for this would be that we basically export the whole model and just cut the model in the 3D model. So it just depends on how it would look like, but the parametric approach would be to use the construction schedule, because it will also apply, it will also adapt to any change that happens to the alignment or to the geometry. So the next step, where I'm going to share a few tips and tricks about foundations and how to make better use of the modeling foundations. So about modeling foundations, we know that sometimes we have, let's say, at our foundations, we have a lot of piles. And we know that the process to create a pile is to create for each pile a circular cross-section. But by making use of the external boundary tool, we can easily model a group of piles. And of course, what we're going to see here in the next step of these foundation parts of the presentation, we will see how to create piles that are ready for analysis, how to make a realistic simulation of the soil around it, the supports of the soil. So we will just see this in the next part. So the first part will be pile foundations with the use of the external boundary functionality. For this workflow, what first needs to be created is one pile cross-section that can be reused on the model. But how do we do this? We created a pile cross-section with a diameter, now in this case, 1.2 meters. We just create one cross-section. We do not need to apply any structural unit to this. We just have this one cross-section sitting in its own cross-section window. And this cross-section of the pile will be reused all over the model. Of course, we also need the pile cap. And this pile cap is also prepared in a separate cross-section window. We have defined some values. I think the whole, let's say, width of this pile cross-section is around 24 meters. And let's say the height, in this case, which will be in the y direction, in the y local direction, will be around 7 meters. So we have these two cross-sections now prepared, but how do we, in the easiest way possible, place these pile cross-sections on this pile cap cross-section? We need to make a few steps of preparation to prepare this. So once the pile cap cross-section is created, we need to apply boundary lines to easily place the piles along the intersections. Because we can make use of the external boundary functionalities on placing this external boundary on an existing boundary. And you will just see in a visual representation what I would like to tell you with this. So at this point, we have this pile cap cross-section. We make use of the boundary tool functionality. And as we see in this case, we have created boundaries that are just vertical lines, and they will serve as guidance lines on which ones I can place these pile cross-sections. And by using this external boundary tool, we can then easily place multiple piles into position. And how do we do this? First of all, we have these vertical boundary lines that we have created in the previous step. Now we see in the boundary tools window, we make use of the external boundary tool. We select this feature, we activate this function, we select an intersection, pick the existing cross-section of the pile, place it in position on the farmost left side as we see on the right picture, and then we have this property window where we see at the point at the chapter of reference where we can set up copies, offsets, and spacings. And as we know what the spacing should be like, and we know we need 3 copies, we can easily just type this in instead of 3 times modeling the same pile cross-section. And once we have defined 1, we can make use of the copy function, and then we can easily distribute the same sets of piles on the cross-section. But it doesn't need to be the same sets of piles, because we will see on the first vertical line, we will have 3 piles, on the second one, we will have 2, then we will have again 3, then maybe we will have 1. And this can be just easily changed by changing as an additional copy to just change the number of copies and change, for example, either the offset or the distance between them. So we see once we click on this external boundary that has been placed in our main cross-section, we see that we have this copy icon that is directly positioned near the element, so we have quick access to it. So this is just a small helping toolbar that helps you to work with this. And once we make use of these copy changes, we can see that we can create this group of piles in a really fast way and effective way. So we now have not 1, but we have 2, 3, 4, 5, 6, 7, 8 groups of piles that we have created in a matter of seconds by just preparing the initial model. But of course, we can go further on with detailing. So we would like to say the furthermost column of piles on the left side and on the right side should be inclined. What do we need to do this? How we do this? We apply variables to it. As we see on this image, we see that we have created a variable named distance, which will define the position of the left group of piles. We did the same for the right one. We created a small variation table, just a simple one, which will define that, let's say, underground at minus 18 meters, the distance should be 6 meters. And then once we get nearer to the top at minus 2 meters, it should be 3 meters. We apply these changes. We apply this variation table to our expression here with the variations, and we get this nice representation of the model. So now we're going to simulate pile foundations. And for this example, we created a simple pile foundation with a reference point for soil support. So this would just be one model now. This will be just one pile. And first of all, we extrude this into a 3D model. Once we have this 3D model prepared, we apply material values to the pile for a correct analytical model. So we have decided to use just one type of concrete in this case, so C25 through 30, according to the Eurocode standard. And once this is applied, we see on the image on the right side, we see our analytical model where we have this automatic numbering of nodes and automatic creation of the analytical model. But what is the important part here, what we would like to show is the definition of soil supports and stiffnesses. So we have our model. The analytical model is now created. Now we make use of soil supports of these structural connections. And first we place one structural connection just at the bottom of it. In the next step, we use the copy function to copy all of these soil supports to the sections of our pile where we need them. So from the bottom to the top, where we would like to represent some kind of foundation, some kind of soil structure interaction. And by using multiple select in geometry tree, we apply these changes to all the desired soil supports. We can select multiple soil supports at the same time. And as you see that we have defined for all of them but the last one, we have applied different stiffness values that we just have as stiffness values in the global Y and Z direction. But what happens if we have multiple piles that need the same definition of these soil supports? Do we need to create them all over again? No, we don't. Because we can use copy and multi-select, we can apply these soil supports to also to another pile, for example. So by just using multi-select, by clicking the Shift button and using this multi-select tool, we can then just easily copy all of these objects to another pile. But you might think this is the finished part, but no. So if we would like to round up this whole detailing process, we also need to place reinforcement parametrically. So for example, in this case, pile reinforcement. And by this, we make use of our new Python parts technology. You will see this in a nice video representation that was also featured on the Bridge Day. That was on the 20th of May, if I'm not mistaken. But for all of you who have missed it, you have the possibility to download the recordings of Bridge Day. We see that once the Python part is created, we have access to all its parameters already inside Allplan Bridge. And then by using this Python part placement, we can easily position this pile reinforcement here on the object. So once we recalculate this, the model has been applied to the Allplan Bridge model. So the reinforcement has been applied, has its defined position in Allplan Bridge. But now we will also see that this reinforcement will be created. As we see on the left part of the model, we see that this reinforcement has been created also in the detailing model in Allplan Engineering. But we don't stop at this. As you see, we can also create section view, and we can easily go into automatic drawing production by using this Python parts technology that has been implemented in the latest release. Okay, for the last part of the presentation will be something else than infrastructure objects. So this will be cooling towers. And I think this will be also very interesting to see. So we know this extensive parametric modeling functionality can also be used for creating non-infrastructure objects as cooling towers. It's a bit more of a different approach that's required because we do not rely on the main longitudinal axis as we do with other objects like bridges, roads, or tunnels. But we are focusing here on using the vertical elements known as piers in Allplan Bridge. As said, we don't rely on the main longitudinal axis, but at least one point main axis is required for setting up reference points that will be used as connection points for the pier. But in another way, the main axis can represent the ground plane in the model on which the cooling tower will be positioned. So for example, we have set up a nice ground plane. Once we extrude it, we get this nice plane representation, let's say this foundation representation where our cooling tower is going to be positioned. But now here comes the interesting part. Once the reference plane has been created, To position the object, we require a circular cross-section for the cooling tower. For this, we make use of the circular boundary functionality, but we will require two circular cross-sections for this model. One will represent the outer edge, and the second will be required to define the wall thickness. Once we define both the circular boundaries, we make use of Boolean operations in Allplan Bridge to remove the inner boundary from the outer one. So these are now both circular cross-sections placed. The use of Boolean operations has not been made yet, but by removing the inner one from the outer one, we get these nice cross-sections, which looks like a nice tube. But of course, we need to apply further on variations to get the correct shape of the cooling tower. So once the cross-sections are prepared, instead, a variation needs to be prepared to achieve the desired geometry of the cooling tower. This can be done in table form as parabolic or linear transitions. It can be also done as formulas, but I have decided to show this one possibility, how to do it with tables in table form. So it can be either done by placing a variation table as you know it with a parabolic transition, so how your shape would look like. Just to imagine it, I would turn it by 90 degrees and look at it in a vertical way. Or the same can be achieved with a linear transition, but then we would have to have much smaller point distances between them. So at this point, once we have created these tables, the variations are now ready to be applied to the model. So this is now the first tube that we have extruded. And now in the second step, we have applied these variation tables for the outer diameter and the inner one. And once we apply to this, we get this nice applied variation of the shape of a cooling tower. But this is not the end of it, because we know that one of the most important parts of the cooling tower is not its shape. Basically, it is its shape also, but it's also the air intake at the bottom of it that we also need to model. And this is something that we can also easily do in Allplan Bridge. So now we come to the air intake modeling and preparing the cross-section. First, in the first step, we are going to define a circular cross-section. By using the circular cross-section boundary tool, create just a simple cross-section. Now we need to create an external cross-section for the air intake columns. And we will make again use of the external boundary tools. So this is now just a simple, let's say, with width of 0.5 meter and the height of 1 meter, a simple cross-section that will be applied through the external boundary tool. We apply this now on our circular cross-section by using the external boundary tool, and we get this nice column positioning around our circular cross-section. And as we've seen before, we can also apply the number of copies, and we can apply a different spacing. But a few more steps will be taken here to achieve the correct spacing if these elements are, for example, if the radius or the diameter of the circle is changing. So this will be seen now. As we said, the radius and spacing variable needs to be defined and applied to correctly display the air intake. So we have applied the spacing variable here. And for the spacing to be correctly displayed with the changing radius, we need to describe the following change of geometry as a formula. And for this, we have two ways. We can either define a formula on its own, or as we see here, we can already type in this expression to get the correct spacing. We will just calculate the circumference of the circle and then just divide by the number of elements that we're going to place to get the correct spacing. So this is now the applied variation. And we see that at the bottom, where I have decided the height will be, I think, 5 meters for the air intake, we see now this nice inclined geometry of the air intake columns, which we see at the bottom. Of course, as with any other model, we can also export this model into Allplan Engineering for further detailing. So this is the model then in Allplan Bridge prepared to be exported with its ground plane, exported into Allplan Engineering. We can create sections and then just do additional detailing on the sections. At this point, I would like to thank you for your attention during the webinar. You can get in contact with us. Here you have our contacting email address. It's the best you type directly at support@allplan-infra.com to get in touch with us. And of course, also at this point, I would like to invite you to our next advanced modeling webinar, which will be the last part, the fourth part. But we are not sure exactly about the date yet, so this will be announced. So thank you again, and bye-bye.